Okay, so this is Transports Exam 3, Part 1. So to start, we are given a bar, and this bar is going to have a length of 50 meters. And we are also given that the initial temperature of the bar is 50 degrees Celsius, and the end of the bar is perfectly insulated. And then so the initial temperature of the rest of the bar is 20 degrees Celsius. We're also given that our change in distance is 1. We also have 50 pieces, and our change in time is 1 second. And if we want to convert that to seconds per hour, that's going to give us 3,600 seconds in an hour. And then we're also given that our alpha is equal to 1 meter squared per second. And then so basically what we want to do is we're going to try to be determining our change of temperature according to time. And this is equal to our alpha multiplied by our temperature of x squared. And then we can further this to our temperature at position J, and plus the next one minus temperature of that same position at the original. And this is all over our change in time. And then this is equal to our alpha times that temperature to the next position, n, minus 2 at the original position, n, plus t to the previous position, n. And then this is all over the change in position squared. And then just to make things easier, we're gonna have an r variable, and we're gonna make that equal to our alpha times our change in time over change in position squared. And then if we take this variable and use it to replace this within this equation, and we're also going to go ahead and multiply our change in time over to the other side, we're going to get t of the initial position to the previous, or next one, t to j, the original, is equal to our variable r, all multiplied by t to the next position, and minus 2 t of the original position, n, plus t of the previous position, n. And then so basically, even though we created this variable r here, what this is going to do is later on, if you were to use this equation, this r is going to end up causing some issues. So what we're going to do is we're going to use the Crank-Nicolson, and basically what this does is they're taking the average of the values at the same position, but just at the times on both sides. So with this, what they do is their r is going to be equal to alpha times the change in time over 2 times the change of the position squared. And then so if we do that and do the algebra and go ahead and plug this in, what we're going to get is we're going to get negative r times t, previous position, plus 1 plus 1 plus 2r times temperature at the initial position and to the next one minus r times temperature at the next position and at the next one. And then this is all going to be equal to r times temperature at the previous position to n plus 1 minus 2r times temperature at the original position n plus r times t at the next position n. And then so now what we have to do is we're going to want to make a matrix in order to solve all of our unknown variables. So to start, we're going to start with our positions. And then so we're going to start with j equal to 0, then j equal to 1, then j equal to 2, and then basically this continues. So the first one, basically we're just going to take the coefficients of this side of the equation. So we're not going to start with 0 because we're going to get to that after this. So we're just going to go ahead and start with j equals to 1. So if we look at these, we're going to start with negative r, then 1 plus 2r, negative r, and then the rest will be zeros. And then basically for the next one, this all just shifts over 1. So this one will be 0, this one will be negative r, this one will be 1 plus 2r, and then this will be negative r, and the rest zeros. And then basically this is going to be multiplied by our temperatures. So this, and then so we're going to just, again, we're going to start with 0, 1, 2, and then again this just continues. So then this is going to be equal to our other side of the equation. So then this matrix is going to be, again, we're going to start with 1. We're going to have our coefficients on this side. So we're going to have r previous n plus 1 minus 2r times t to the initial position n plus r times t to the next position n. And then this is the same for the second one, and this also continues. Then, so we want to help determine our left boundary. So to do that, we're going to take, so because everything right here is known, so we're just going to go ahead and multiply that to the other side. So for our left boundary, we're going to have 1 plus 2r t to the initial position, n plus 1 minus r t to the next position, n plus 1. And this is going to be equal to r t of the next position, n plus 1 minus 2r t of the initial position, n plus r t to the next position n plus r t to the previous position n. And then so with this equation, this is where we're going to go ahead and go back, and this is when we can plug in our matrix values for j of 0. So if we look at this side, and this is going to start now with 1 plus 2r, then it's going to be negative r, then 0, and then the rest will be zeros. And then we are assuming that t of the initial position is equal to t of j to the next position. So this is going to help us while we determine our last boundary. So when we do that, we're then going to get negative r t to the next, or the previous position, n plus 1 plus 1 plus rt of the initial position n plus 1 is equal to r t to the previous position n plus 1 minus r t of the original position n. And then so now looking at this equation, we can go ahead and plug in for our last boundary. So looking at this side, we know this is going to be zeros, then we're going to have negative r, then it's going to be 1 plus r, then it's going to be 0. And then also then looking at this side of the equations, we can go ahead and plug in the last boundary for this part of our matrix, which is going to give us r t of the previous position n plus 1 minus r t of the original position n. And then so what we're going to do is we're going to use this to help determine the preceding temperatures to determine the next one. And now I'm going to move on to part 2, which is the Python.